All right, let's talk about a problem that, every single developer hits at some point. How do you build one container image that just works? I mean, everywhere. On your laptop, in the cloud, no matter what CPU is humming away inside.
So, have you ever seen this? Exec format error. If you have, you know that feeling. You've just crashed headfirst into the invisible wall of multi-architecture computing. It's such a frustrating error, and what it really means is there's a deep, fundamental mismatch between your app and the machine that's trying to run it.
This is really the 21st century version of that classic line, right? Well, it works on my machine. But here's the twist. This time, it's not about some missing library or a wonky config file. No, this goes way deeper. We're talking about the physical silicon, the actual CPU architecture.
Okay, so to figure out how to solve this, we've got to understand why it's happening all of a sudden. I mean, for a long, long time, the computing world was, well, it was a lot simpler.
See, for more than a decade, things were easy. Pretty much every developer laptop and every server in the cloud ran on the same architecture, x86-64. But that monoculture is over. It has completely collapsed. With the rise of these incredibly powerful and efficient ARM64 chips, like Apple's M1 and M2 chips for us developers, and AWS's Graviton processors in the cloud, the landscape has basically split right into.
So, how in the world do we build software for a world with two major, totally incompatible CPU types? Well, the answer is this really beautiful and elegant concept called a multi-architecture image.
This right here, this is the secret sauce. Instead of an image tag like My App Latest, pointing to just one image, it points to a special kind of list, an index. Think of it like a table of contents. It basically tells the container runtime, hey, listen, I've got a version for ARM over here, a version for Intel over there, and who knows, maybe even a few others.
And if you look under the hood, this index is really just a simple list. You can see here, each entry points to a specific image using its unique fingerprint. We call that a digest, and it clearly labels what platform it's for, like AMD 64 for Intel systems or ARM 64 for Apple Silicon. And this is where the magic happens, all behind the scenes. When you type Docker pull, your Docker client says to the registry, hey, I'm running on an ARM 64 chip. The registry sends back that whole index, your client scans it, finds a line that matches its own CPU, and then boom, it pulls only that specific version. It's this seamless, totally automated negotiation that happens in seconds. Okay, so that negotiation is fantastic for pulling images. But what about creating them in the first place? How do we even make these things? Well, the modern answer is a tool called Docker buildx. You can think of buildx as a supercharged replacement for the good old Docker build command. It's a plugin, and it hooks into this next-generation build engine called buildkit. And its entire reason for being is to handle the complexity of building for multiple platforms all at the same time. And let me tell you, buildkit is a huge leap forward. Unlike the old builder that just went line by line, buildkit looks at your entire Docker file at once. What does that mean? It means it can run independent steps in parallel. It's way smarter about caching layers. And most importantly for our conversation today, it was designed from the ground up to manage builds for different platforms, all from a single command. All right, so buildx gives us this incredible power to build for multiple platforms. But how it actually does that? Well, that involves a choice. There are really three main strategies you can take, and each one comes with some pretty critical trade-offs. Path number one, the easy way, is emulation, using a tool called QEMU. Now, this is a really clever piece of software that lets your Intel machine basically pretend it's an ARM machine, or the other way around. It lets you execute code for a totally foreign architecture right on your own computer. And here's the crucial thing about emulation. It is incredibly easy to get started. I mean, you literally just add a -platform flag to your build command, and it just works. But, and this is a big but, that convenience comes at a very steep price: performance. Emulation is basically translating CPU instructions one by one in real time, and that is super computationally expensive. And this really shows you just how severe that slowdown can be. I mean, look at that. A build that takes maybe 2 minutes to compile natively can easily balloon to 20 or even 30 minutes when you're using emulation. For really simple stuff, maybe that's fine. But if you're compiling code, oh man, it is an absolute productivity killer. So to get that speed back without having to buy a bunch of extra hardware, we can turn to path number 2, cross-compilation. This is a really cool technique where your native CPU runs a special kind of compiler, one that knows how to generate machine code for a completely different type of CPU.
This is the high-performance path, for sure. It's especially great for compiled languages like Go or Rust. The build just flies because it's running at native speed. You're not emulating anything. The catch? Well, you have to actually change your Docker file to be platform aware, and that definitely adds a layer of complexity. All right, now for path number 3. For the absolute ultimate top-tier speed and reliability, especially in a professional setting, you can set up what's called a distributed build. Think of it as a build farm. You have different machines for each architecture you want to build for.
This is really the enterprise-grade solution. From your one machine, you can run a single buildx command that orchestrates builds across a remote Intel server and a remote ARM server, all at the same time. You get the fastest possible speed, zero emulation, total reliability. But it comes at the cost of having to manage all that extra infrastructure.
So, there you have it. 3 different strategies. But the real question is, how do we apply these effectively in a real-world automated CI/CD pipeline where, speed and reliability are everything?
Well, a really common mistake, we'll call it the QEMU trop, is to set up just one CI job to build all the platforms. And what happens? The slow, emulated part of the build holds the entire pipeline hostage. It's awful. The real best practice is what's called a matrix build, where you build each platform in its own separate parallel job.
And this pattern is so powerful. You can see it here. You have parallel jobs, job A and job B, building for each platform as fast as they possibly can. Now here's the key. Each job pushes its image to the registry using its unique hash, its fingerprint, not a tag. Then a final super quick job comes in, grabs those hashes, and creates that final manifest list with the tag. It's incredibly fast, super efficient, and beautifully decoupled.
Okay, so to wrap this all up, what are the key takeaways? First, that exec format error is your classic sign of an architecture mismatch. The fix, a multi-arch image powered by an image index. Remember the trade-offs. Emulation is easy but super slow. Cross-compilation is fast for compiled languages but adds complexity. And for your CI/CD pipeline, that parallel matrix build is absolutely the way to go to avoid the QEMU performance trap. Look, the future is heterogeneous. Our computing world is just going to keep diversifying from ARM-powered clouds to all sorts of new architectures at the edge. Building for just one platform, that's not really an option anymore. So the question is your build system ready for this? Because mastering these patterns is quickly becoming a non-negotiable, essential skill for every single modern developer. Thanks for joining this explainer.